Welcome to the lecture of the course Biocontrol Systems. This lecture focuses on example problems in modeling of mechanical systems. In the previous lecture, we have seen how to model a mechanical system. We will try to take an example and derive the transfer function for a given mechanical translational system. Let us consider a system with a mass element 1 fixed to one end has a viscous friction coefficient connected to the mass element represented as B and supplied with a force F of t as the input. Because of the force F of t, there is a displacement x of t. The question might be, derive the transfer function for the given mechanical system. The possible transfer function is x of s by f of s. Let us consider the free body diagram of the mass element m. The force F of t is applied based on the principle of D'Alembert's. There will be an opposing force acting on the mass element, which is the force on the mass element itself, represented as Fm, and the force acting on the viscous friction coefficient element, which is connected with the mass element m, which is represented as Fb. So the applied force will be equal to the opposing force represented as Fm and Fb. These two forces can be represented as m into d squared x of t by dt squared plus b into dx of t by dt. Let us consider this as equation 1. This is the modeling equation governing this particular mechanical system. Our aim is to derive the transfer function from this equation, which is in time domain. So applying Laplace transform to equation 1, we rearrange that equation as f of s is equal to s squared m into x of s, considering the initial conditions to be 0, s into b into x of s. Since I find x of s to be common, the equation can be rearranged as s squared m plus s into b. The required transfer function is of the form x of s by f of s, which can be written as 1 by m s squared plus b s, or 1 by m divided by s squared plus b by m into s. So the actual transfer function for this system might be 1 by m into s squared plus p by m into s. If we extend our discussion for a system which is having two mass elements as shown in the figure m1 and m2, and there are different elements like viscous friction coefficients and the spring constants connected in such a way, we are supposed to derive the transfer function for these system. The possible answer is being expressed here. Let us try that. In that case, we first try to derive the differential equations governing that system and then applying Laplace transformation to find the transfer function. Since we have two displacements available here, that is two outputs available here, we are supposed to find transfer function which is a single input single output representation. So out of these two outputs, the actual transfer function will be represented based on the mass element which is actually receiving the force f of t. In that case, in this system, the force is applied to m2. So the actual transfer function for this system will be in terms of the displacement x2. So x2 of f by f of s is the transfer function what we are supposed to derive. So let us consider the first mass element. Since we have two mass elements, the number of differential equations will be 2. Let us consider the first mass element m1's free body diagram. The components connected to that mass element m1 are the m1's force itself, then the viscous friction coefficient B1, the spring constant K1, and there is a connection between M1 and M2 through the mass element, the viscous friction coefficient B and the spring constant K. That is, they are common for both M1 and M2. So obviously, combining all these forces, the force on the mass element M1 itself, then the forces acting on these bodies, we can write the force equation to be 0 is equal to, because we are not having any direct force applied to M1. So the force acting on this mass element M1 will be equal to 0, applied force. The opposing forces will be the force equations on that particular element, which can be represented as M1 into d squared x1 by dt squared plus k1 into x1 of t plus b1 into dx1 of t by dt, because these displacements are only considering only available for the mass element m1. But when you see these components b and k, they are common to both m1 and m2. So they might be represented in terms of the resultant displacements. So b into dx1 by dt minus x2 by dt, so d by dt into x1 minus x2 plus k into x1 minus x2 will be those terms. Since we are considering m1, the primary displacement has to be x1. Similarly, we can write the force equation for m2, as we know that now the primary displacement is x2 and we have directly applying a force to the mass element m2. So f of t is equal to m2 into d squared x of t by dt squared plus b into t by dt x2 minus x1, since x2 is the primary displacement, k into x2 minus x1 plus b2 into dx2 by dt. So these two equations are the governing equations for the given problem. So taking Laplace transformation, if you want to find the transfer function for both the equations, we get 0 is equal to m1 s squared x1 plus k1 x1 of s plus s into b1 x1 of s plus s into b x1 of s minus x2 of s plus k into x1 of s minus x2 of s when you are considering the first equation. And similarly, we will get another equation if you are taking Laplace transformation for equation 2, which is given as f of s is equal to m2 into s squared x2 of s plus s into b x2 of s minus x1 of s plus k into x2 of s minus x1 of s plus b2 into s into x2 of s. Let us mark these two equations as equation 3 and 4, and we can find the displacement x1 common in some of the terms and x2 common in the some of the terms. So rearranging that equations and considering x1 and x2 common in some of the terms, we can get equation 5 and 6, which is shown in the below equations 5 and 6. So from these two equations 5 and 6, we are supposed to find what is the transfer function x2 of s by f of s. We have multiple ways to find that. The unwanted parameter or the parameter to be discarded is x1 of s. So we take the equation 5 and try to find what is x1 of s. Then substitute that x1 of s in equation 6. Now the equation 6 will be in terms of f of s and x2 of s. After manipulation, we end up with a transfer function x2 of s by f of s is equal to m1 s squared plus s into b1 plus b plus k1 plus k. And in the denominator, we have the terms minus sb plus k the whole square plus m2 s squared plus b2 plus bs plus k, m1 s squared plus s into b1 plus b plus k1 plus k. We can stop with this level, or we can still further expand the equation in both numerator as well as denominator, and we can find some terms gets cancelled.